We are going to do logarithmic differentiation. We know logs are quite important. They help us create bonfires.
Wait, what did you say?
Too late, don't pay attention. I said logs are quite important. They help us create bonfires.
Oh.
Will we be learning how to?
Well, I thought we were just using them to keep it in the class.
Ah, that was good.
I thought we were just using them to keep afloat in the class.
Wow. We know that ln of x is natural logarithm. Log of x is base 10. In the sense, it is log base 10 of x and log base e of x.
Log base e of x. Lovely.
Right? Instead of writing it as log base e, we'll just call it as ln because it's natural log. Instead of calling it as log base 10, we'll just call it as log x. If we have any other log, say some b, then we could write it in terms of natural log as ln of x divided by ln of b. Good. So those are things that you should know from Unit 1. Before we start, make sure you understand the properties of logarithm. Quite important. If you had forgotten, go back, review. We'll do some problems, hopefully it comes back to you. So, just like implicit differentiation, logarithmic differentiation is a technique that will make differentiation easier because logs tend to make things easier. Start with a basic case. Suppose we have y equals b raised x. It is not natural number or natural log e, rather it's a different b. Right, b could be 2, 10, 15, 100. B is any number other than e. Good? So it's not e raised x. We want to find the derivative. Of course, we could take the difference quotient approach and do all kinds of things, but we're not going to. I'm going to take ln on both sides. So ln of y would equal ln of b raised x. Yes, we call it logarithmic differentiation because we take ln on both sides to make things easier. What property can we use here?
I'll take the x.
The x comes to the front. And you have x multiplied by ln of b, right? Now ln of b is a number constant because b is a constant. Do we agree? So now I want to differentiate on both sides. So we are going to take the derivative on both sides. And note the derivative of natural logarithm is just 1 over x. Clearly, x cannot equal 0, because if we go to infinity. Okay, if I take derivatives on both sides, let's say if you understood implicit differentiation, make my Friday better.
You can certainly go.
I wanted to find the derivative of ln of y. I told you the derivative of ln of x is 1 over x.
Meaning that if we apply this. Meaning that if we apply this.
So close.
Y prime over Y.
Y prime over y. If I treat that as x, the derivative would be 1 over y. But then I realize that it's y, which is a function of x. So I multiply by y prime. Good. On the right hand side, ln of b is a constant. What is the derivative of x with respect to x? 1. So that's it. We want to solve for y prime, so y prime will be equal to y multiplied by ln of b. Yes, but what is y? We'll go back to the very first step. B raised x. So we just showed that the derivative of b raised x is b raised x multiplied by ln of b if b doesn't equal e, the natural exponent.
So I understand the very least how you've got here. But however, how did you get ln of b as the derivative of x ln of b?
Constant
Oh,
comes out. What is the derivative of x with respect to x?
yep, that's what I thought. Sorry about that.
So that is the sort of formula. The entire reason as to why we learned implicit differentiation is to do that. From here to there.
Oh, if there was a number instead of 1 in front of the x, would it be the number ln b?
Yes. So if you had a 4 here, you'd multiply everything by 4. Did I say that? The hand go up? No. So, great. Now that is the general formula for the derivative of an exponential function. When I started here, I said b is not equal to e, but suppose, hypothetically, it's not going to kill us. So suppose b is equal to e. Yes? Then we want to find the derivative of y equals e raised x. Agree? B becomes e, so e raised x. What is the general formula for the derivative of an exponential function? This is the formula we arrived at, yes? So if I replace b by e, I will get e raised x multiplied by ln of e. But that seems incorrect. We know the derivative of e raised x is e raised x. But I end up having e raised x multiplied by ln of e.
The squiggly line.
1. Squiggly line, yes. Make it squiggly. So e raised x. So that's why we call that the generic or general version of the derivative of an exponential function. Good. Of course, there are other ways to arrive at the same result, but I'm not going to bore you with all that. Are we clear? Yes. I said I'm going to start simple, So here it is, y equals ln of sine squared x. And we want to find what log.
I was just about to say it's gonna pull out the trigonometric.
Right, you may look at this and say, just like I said, we're going to start simple, and that seems very complicated,
You could easily make
right? But anytime you see logarithms, may it be natural, may it be a different base, first thing that has to come to your mind is using properties. I could write sine squared x right? I'm using brackets to distinguish. Yes? Did I do anything wrong? No. What rule of logarithms can I use? I can move that 2 to the front. So y is simply 2 ln of sine. Good. That's the best we can do. We can now take the derivative. Two as is. If I treat sine x as just x, what is the derivative of ln of x? Oh,
1 over x.
1 over x, ln of x. Yeah. So 1 over sine x. But then you realize that that is a function of x. So now we multiply by cosine of x. What rule did I use? Chain. You can leave the answer as is, but if you observe carefully, cosine over sine is cotangent. So 2 cotangent x. Good.
And the 2 stays there because of property logarithms, right? 'Cause when it
Yes,
comes to
that's
derivative.
Yes, because there was a 2 here, and that's why.
So you take it out, so you almost ignore that when you do the derivative of ln of x.
Yes.
Okay.
Are we clear? Okay.
So then you can y.
So one question? Yeah.
Oh, no, we're talking about, okay.
So what is ln x e raised to x? And you look at that, the first thing that comes to your mind is, well, what comes to your mind? Immediately you would go for chain, correct? So you would look at whatever that is inside, and you will say, well, I'll treat that as x, and 1 over x e raised to x, take the derivative of the inside. What rule should you use to find the derivative of the inside product? Now that's awfully painful. Definitely. So the very first thing to ask yourself is, could you simplify the expression before you start? Yeah. Well,
Could you just take the 2 and
no, you cannot. Deanna asked a good
it
question.
wouldn't be something as a 2?
Can I simply pull the 2x to the front? Not yet. You can pull the power out if there is only a single term inside the logarithm.
Because it's not a constant.
There are 2 terms in here, so you cannot pull that 2 raised x out.
It's like trying to.
Previous example, sine x was by itself, so I was able to pull the 2 out. If there was, say, an e raised x here, I cannot do that. Good. So there is a rule of logarithms that I can use.
As long as the exponent.
Split them apart because we have ln of x times e raised to x. So that would be ln of x plus ln of e raised to x.
Now.
Yes?
Okay.
What happens to the ln and the e?
Oh, they cancel.
So y is simply ln of x plus 2x. Yes. What is the derivative of ln of x? What is the derivative of 2x? That's it.
That's it.
Wow. That's not good.
The power of
Yes.
properties.
Why did you cancel the ln e again? Is it because the ln x?
They are inverses of each other.
Oh, okay.
ln would always cancel e would always
That makes
cancel.
sense.
Does anyone
What
here
would
look
happen
at
if x was x plus e to x?
Oh, good question. What would happen if we had x plus e raised to x? That will be tough.
Oh, so we have to go through the same process?
Yes, we cannot split it up. If we have x plus inside, we can't split the logarithm up. Good.
What would you do?
So, come again?
Could you like do it or no?
I'll do an example.
You know, thank you, Joe. That's a good.
So, what seemed as a difficult problem at the very beginning, in fact, is an easy problem.
So
Right?
having the log allows us to bypass going through chain law. and
Yes.
product.
Exactly. It helps a lot in terms of simplifying.
Can we add logs to anything?
I know, right?
Huh?
Can we add logs to anything we want?
Sure, depends on the problem. For instance, going back to your question, if you have x plus e raised to x equals y, it would be foolish to use logarithmic differentiation. Do you agree?
Yeah.
If you took ln on both sides, you would have ln of y equals ln of x plus e raised to x. Correct. You can differentiate it using implicit differentiation, but when you come here, you have to use chain rule and then product rule, bunch of other things, correct? But you could have just taken the derivative of that directly. See the difference? So sure, logarithms play a significant role in producing the word, but you can't just apply to anything you want. Sometimes you're going to make it hard.
If you try to use pliers or you should have hammer, it's just gonna make the.
Exactly.
I don't know why I'm sorting my words today.
Are you dehydrated?
No, but I do have like maybe 5 hours of sleep.
So I am going to do a problem like what you wanted, but not yet. I want you guys to make these two logarithms first.
What causes that?
The dog was somebody.
No, but inside.
Sorry.
So it's just a constant flashbang in the other room.
That's not what flashbang sounds like.
I'll be honest, I only know 100 movies.
So we have log base 10 here, right? So far, we only looked at ln, and I wrote the derivative of ln of x is 1 over x. But the derivative of any other base log is not just 1 over x.
It is going to be something.
So if y is ln of x, the derivative would be simply 1 over x. Good. But if y is any other base other than e, then y prime is 1 over x multiplied by ln of b.
Huh.
Good.
That's lovely.
Just like I had a generic formula for b raised x for any b, which I showed will work out even for e. This is the generic version for a log. So doesn't matter what base you have. If you take the derivative, you always get 1 over x ln of b. you can verify, go back to this. ln would mean the base is e, correct? So if I put e there, I have to put e there. But what is ln of e? Nothing. 1. So 1 over x, you go back to that. Does that make sense? So this is the generic version of the derivative of a log. So how would you go about doing this?
1 over x and then log and the square root of x.
1 over x, that is square root of x. Or you mean to say you would do 1 over square root of x, and then take the derivative?
I think so.
You
That
would
isn't what you was thinking.
convert the root first.
So any other thoughts?
Convert the root first.
Convert the root first. So Gio jumped, to a mistake, which was a mistake. So his thought process was to take the derivative of log base 10 square root of x directly. So 1 over square root of x, ln of 10. Yes, if you treat this as x. And then you multiply by the derivative of root x. Correct. What rule did I use? Chain. But you took a step back. Go with what Annie said. We can convert the root to an exponent. Yes. I can move the root to, the 1/2 to the front because that is a single term. So we will have 1/2 log base 10 of x. Yes.
So 1 over 2.
Y prime would be 1 over 2 times. What is the derivative of log base 10 of x?
It would be x times ln of 10.
X times ln.
Oh, wait, sorry, I mean 1. Wait,
1 over.
well, that's what I mean, like
Oh,
when it comes to
They are
dynamics.
completely different things.
I'm sorry.
So 1 over x times ln of 10. I knew exactly what you were saying. So the answer here is 1 over 2x times ln of 10.
Yep.
Good.
Lovely answer.
So which is easier? So doing chain rule and trying to get to the answer, or using a property of logarithm and getting to the answer? Obviously, this is easy. Yes? Okay, so we want to find the derivative of this. Couple of ways to do it. So you can convert this to 1 over cosine x, take the logarithm, use the property of logarithm. Unnecessary though, because we can use chain rule directly. If I treat this as x, what is the derivative of ln of secant x?
1 over x.
1 over secant of x.
Oh, I'm sorry, I thought we were just talking about 1 over like x as in the ln of x.
Multiplied
Right.
multiplied by the derivative of secant x. What is the derivative of secant x?
So what you would have
Secant x times x.
is secant squared x times tangent x at the end. 1 over.
The secant and secant will get cancelled.
Right, no, I'm an idiot.
So the answer is tangent x. Good.
This is what 5 hours is.
We have to use quadratic rule. So if u is x, v is ln of x, u prime is 1, v prime 1 over x. Yes. So y prime is u multiplied by v prime plus v multiplied by u prime. Good.
Oh, wait, no, sorry, I think quotient. What the hell am I
The
talking?
x's will get cancelled, so we have 1 plus ln of x. Good. If I asked you what is the second derivative, what would you tell me?
1 over x.
1 over x. So derivative of 1 is 0, derivative of ln of x. 1.
When, like for those who have to take calc 2, will you get more into double derivatives and that stuff? And I know we have learned as many double derivatives. That's just
Yeah, we will do more in chapter 4. So that we'll learn something called concurrency. We can't do that now.
So, sir, how come at the very least, we haven't practiced much second derivatives?
I just thought so we will do that.
Oh, okay.
We'll do more. It's easy to go from here to there, but to do it repetitively, we will do it.
Thank you. I was just wondering because it was on the exam more so than it has been on a lot of what we've been doing here. Because
So.
also, because my last teacher, or not teacher, professor, didn't exactly answer. If you fail a class, do you still get the credit hours?
Okay, so this is a scenario that Gio was talking about. What if we had x plus something? The most common mistake would be to readily split it up and write it as ln of x plus ln of square root of x squared minus 1. Wouldn't that be nice? But not that easy. You can only split a logarithm if terms are in the product or in division. If it has a plus or minus, that's it. It's going to be difficult. Yeah.
Would it be difficult as in all we have to do is like 1 over that times the derivative, and isn't that it?
Yeah.
And you could get the derivative pretty easily. You could just do 1 plus, let's see, over here at the very least, you'd have to use chain rule.
So there are a couple of ways to do this. I'll do both methods so that you understand. But you can choose whichever one you like. So one is straightforward, which would use chain rule. The other would use implicit differentiation. Once again, I'm going to fulfill Gio's wish.
Yeah.
So why? We can't split this up. So y prime, I have to treat that as say some u. Right? So what is the derivative of ln of u? 1 over u, but u is x plus square root of x squared minus 1. Yes? We want to multiply by the derivative of this function using chain rule. Yes? Now, I'm going to do it separately because it's going to take more space. X plus square root of x squared minus 1. Before we proceed, what should we do?
No, he's correct.
Okay,
You should do the thing where you get the power, like 1 over half.
I'll do the thing. So
I don't know the name, I know.
change it to an exponent.
I was right.
For 1 half.
X squared minus 1 raised half.
Are you talking about just converting it?
Yes.
Oh, okay, but you said it was just like.
Now, I want you to find the derivative of that. I know you can do it.
Alright.
Okay, so we want to take the derivative here. Derivative of x is just 1.
1 plus 1 over.
So what would we use to find the derivative of x squared minus 1 raised half? We have to use chain rule again because it's not just x. So if you call that u, the derivative of that is 1 over 2 u raised 1/2 minus 1. 1/2 minus 1 is negative half. And what is u? X squared minus 1. Are we done yet though? No. We have to multiply by the derivative. One of the common mistakes that I noticed as I walked around is somehow this 1/2 went inside negative half exponent. It cannot, stays outside.
Why doesn't it? Like, why can't?
That's algebra, GA.
Okay.
So the half and the 2 will get cancelled. So we will have 1 plus x squared minus 1
You know, I made a major mistake.
raised half times x. Yes? One more step, we can move that x squared minus 1 raised half to the denominator.
Or should I start that as x plus?
Yes, that was it.
Nice, it's actually going to get simplified further. So I can rewrite this as a radical, but before I do that, well, let me just do that right.
In that now you have 1 over x plus square root
Good so far? Yes?
minus 1.
Could I combine the 1 and x with the square root of x minus 1?
Change the denominator.
Change the denominator. So multiply and divide by x squared minus square root of x squared minus 1 plus x over square root of x squared minus 1. So when I walked around, I said, we can just leave it as is, but as I started doing it, it clicked that this can be simplified. Instead of leaving it like this, if I did this step, a term will get cancelled. So if I combine, I will have x plus square root of x squared minus 1 over square root of x squared minus 1. Yes? That is the derivative part, which I'm going to plug in there. Good. With me so far. That is correct. So I can cancel this term and that term and to erase this part. And I'll simply have y prime is equal to 1 over square root of x squared minus 1. In my vector sign or the exam, that will be the answer. So the key here is to recognize that simplifying the, finding the common denominator here will help you simplify at the end. So I would recommend if you only have 2 terms, why not just take the common denominator and write it out to see what happens at the very end. Yes.
So wait, how exactly did you go back to 1 on the final? Oh, wow.
So the first step would be to take the exponential on both sides. Or I should simply say, or use a fancy word, exponentiate on both sides. Exponentiate. Yes, just like we take the logarithm on both sides. If you see a logarithm already in the problem, perhaps taking an exponential might help, right? So if I took or exponentiated on both sides, I'll have e raised y equals e raised ln x plus square root of x squared minus 1. Correct?
Yes.
Now, what would happen to the e and the ln? Cancel. Go away. So e raised y would be equal to x plus square root of x squared minus 1. Correct?
Take the derivative of both sides.
We take the derivative on both sides using implicit differentiation. Derivative of e raised y is
EY times Y prime.
very good. E raised y multiplied by y prime. On the right hand side, we have to take the derivative of that term.
You already have it, yeah.
But I already have it from the previous part, right? I'm just going to throw that in there. Oh, that is x squared minus 1. Do make that change. I made a mistake. X squared minus 1. Good. Now I can divide by e raised y or use the fact that e raised y is that term, right? So I can write e raised y. This is one of those problems where once you find the derivative using implicit differentiation, you can revert it back to a function in terms of x. So x plus square root of x squared minus 1 divided by square root of x squared minus 1. Algebra. What happens? It'll get cancelled. So we would end up having y prime equal to 1 over square root of x squared minus 1. Yes. Which one would you prefer? Method 2 or method 2? So I personally would go for method 2 in this problem. The reason being, I kind of go around finding the derivative using chain rule on this side. Because I see a radical, and what if you had a trigonometric function, things could get out of hand. Good.
So now,
What is it just says on it, because you have to still find it.
yeah, I think.
We still have to find the derivative of this term, right? Now, my point being, integral of this, if you had, say, x plus sine x, right? I'm sure you can find the derivative using chain rule, but perhaps using exponential might be easier. Okay, so we have y equals ln cosecant of x minus cotangent of x. How did we go about doing it? Using E, okay.
You can't do it that way, but it's like a lot longer than, because she did it here.
What did you just say?
I found the derivative of the inside.
Mhm.
And I set with 1 over cosecant x minus cotangent x times the derivative.
Okay, that's fine. So what Sarah did is use chain runs, right? Correct? Sure, I can do that, but I'm going to show you a different approach. So cosecant x, I can write it as 1 over sine x. Yes. Cotangent x, I'm going to write it as cosine x over sine x. Good. This is how my mind works. I look at those two terms and immediately I go for the fact that, oh, the sine's going to come here, sine's going to come here. I can combine the two. So since I have a common denominator,
You end up having 1 minus cosine x
over
sine x.
sine x.
And then from there you can use quotient.
Sure. Alejandro says use quotient rule. I'm not going to. There's something else I can do which would make this problem easier. What is ln of A over B? What? Ln of A
No, minus.
minus ln of B.
Ah, yes, I am an idiot. Yeah. Not seeing that. Well, you know what?
Yes, I can do that. Now I can use chain rule. What is the derivative of negative, excuse me, 1 minus cosine x, ln of that term? I have 1 over 1 minus cosine x multiplied by the derivative of that term. There is derivative of 1 is 0, derivative of cosine x, negative sine x. Negative sine x times negative positive sine x minus 1 over sine x multiplied by cosine x. Good.
So what you end up getting is 1/1 minus cosine of x, which is then going to be times sine x.
Good so far.
Good, just
So
coming
So I can simply write the answer as sine x over 1 minus cosine x minus cosine x over sine x. Good. I can take this further by manipulating the denominators, finding a common denominator, combining the numerators. But the purpose of this problem is to demonstrate even if you had cosecant x, cotangent x, if the answers that you see are in sines and cosines, the first thing that you should do is to convert to sines and cosines. So if you don't see sines and cosines as the answer, you can do what Sarah did and take the derivative directly.
Would her answer still be right?
Huh?
Would her answer still be right even if it's not in sine?
Yeah,
But it
Would you
would be
just-
an option.
yeah, on the exam it wouldn't be an option, yes.
So if it was written the other way with using the cosecant cotangent, how would you cancel that out to make sure you get what you got right there?
So
What do you mean by other way?
You'd have to do
Like
something.
it written in with cosecant cotangent instead of sine and cosine,
that is a good point.
just written in different terms.
So what we can do is do what Sarah did. So 1 over cosecant x minus cotangent x, correct? Multiply by the derivative. What is the derivative of cosecant x?
Negative cosecant x cotangent.
Negative cosecant x cotangent x. What is the derivative of negative cotangent x?
Negative cosecant squared x. but it's
Negative
just-
cosecant squared x, and we've got a negative in the front, positive cosecant squared x. Good.
We'll just put that over.
So what you do is you simply have cosecant squared x minus cosecant x cotangent x divided by cosecant x minus cotangent x. Yes, seems like this is the easier approach compared to that. As I said, I just wanted to show the answer in terms of sine and cosine. Why is this easier? What do we see in common in the numerator? Cosecant. So if I pull the cosecant out, I have cosecant x minus cotangent x over cosecant x minus cotangent x. Yes? Correct. Those two will get cancelled. So what is the answer?
It would be
Cosecant x. Now, cosecant x is simply 1 over sine x. So if you go back and take the common denominator and combine the two terms here,
You would have
try
a-
it at home, you would end up with 1 over sine x. So
Would that be the answer that we should?
that would be the final answer for the problem. So the answer would either be cosecant x or 1 over sine x. You can take this approach if you think that things will get simplified, or if the answer is in terms of science and cosines.